Institute of Science. He's a well-known mathematician in the area of harmonic analysis and formerly a student of Stein and at the Institute of Advanced Studies. So he will talk today about decay of Fourier transforms, and so I hope those who are here present will be able to enjoy some of his views on this topic. Thank you.
I will add. I would like to include that I have done many courses with Professor Thangavelu.
But still, you wanted to listen to this talk.
Yes, yes.
Anyway, I will start. Thanks for the invitation and introduction. And then usually the number of people attending my lecture will reduce rapidly, decay rapidly after 1 or 2 lectures. But today, after even before I start my lecture, the number has been reduced quite a bit. Maybe there was no number to start with. So this is on the decay of Fourier transforms. And this is mainly based on several work with my student Preetham Ganguly and maybe some postdocs. And it was Preetham who prepared these lectures, and I already gave this lecture somewhere else. And Preetham has given this lecture at several places. So anyway, let me start. So it's about the decay of Fourier transforms. But let me start with the Fourier transform on the Euclidean space Rn.
You have not shared the screen yet.
I haven't? Oh.
No.
What did I do then? Oh,
yeah.
Yeah, I didn't. I thought it is not necessary. Okay. Yeah, this is decay of Fourier transform. I think now we should be able to see.
If you can make it full screen, it will be much better.
Oh yeah. Yeah, I forgot to do all these things. How do I do? That I forgot. View full screen mode. Yeah. So we have this Fourier inversion formula. So if it's a function on Rn, say integrable function, then the Fourier transform is defined by integrating the function against the exponentials. Then we have this Fourier transform. So, so we are interested in finding functions whose Fourier transforms has enough decay. Given any decay, is it possible to find a function f so that its Fourier transform has a decay? But this is possible because we have the inversion formula. So this is the Fourier transform definition, and just replace, we interchange f and f hat. So f of x will be integrating f hat of xi against e power plus I x dot xi dxi. So if we want the Fourier transform to decay, we can start with any decay, whatever you want, compact support or exponential decay or a Gaussian decay in the case of Fourier transform, then you invert it, and that function will have the property that its Fourier transform has the given decay. So it is possible to construct a non-trivial smooth function whose Fourier transform has any prescribed decay. This is because of the inversion formula. But then this is without any assumptions on the function f itself. But then once you put some restrictions on the function, then this scenario completely changes if we impose more conditions on the function. So let's see. For example, if you want the Fourier transform to be compactly supported, then you just start with any compactly supported function and invert it. Then you get a function whose Fourier transform is compactly supported by definition. But then if you assume that if you impose the condition that the function you get, that also has to be compactly supported, this is not possible because of Pauli-Wiener theorem. If f is compactly supported, then the Fourier transform cannot have compact support. It has to be an entire function. So if the Fourier transform is compactly supported, the function f itself has an entire extension, so it cannot have compact support. Not only compact support, but it cannot vanish on any open set. Similarly, if you want to impose the condition, hello?
Yeah, apart from the Pauli-Wiener, is there some relation for this result to some kind of uncertainty principle, or?
No, I'm just working towards uncertainty principle.
Okay.
Yeah. So for example, so right now I'm just saying that if f hat is compactly supported, then the function f cannot have compact support because of Pauli-Wiener theorem. If f hat is compactly supported by inversion formula, f has to be entire, but an entire function cannot have compact support. So similarly, if the Fourier transform is having this kind of an exponential decay, some constant times e power minus a mod psi, a is positive, then again the inversion formula gives f of x plus iy equal to this, and because of this exponential decay, I can take this complex number in some tube domain, assuming that mod y is less than or equal to a, then this holomorphically extends. So if f hat has this decay, then f extends as a holomorphic function this tube domain, then again f cannot have compact support. So these kind of things are ruled out. So instead of exponential decay, suppose you ask for a little bit smaller, little bit slower decay. So replacing this e power minus mod psi by e power minus mod psi over, say, log of 1 plus mod psi. This decay is so slower than this e power minus mod psi. And suppose you impose this condition on f hat, and the question is it possible to construct a function f which is compactly supported, but still the Fourier transform has this kind of decay? But now with this decay, we cannot conclude that f has a holomorphic extension to some domain. That's not possible because this is lower than the exponential decay. But still, we can ask, is it possible to find a function with compact support whose Fourier transform has this decay? And this question was answered by Ingham in 1934 and in the one-dimensional case. So this is what he proved. So instead of considering the exponential decay, consider a decay of this kind. If hat of psi is decaying like e power minus theta of mod psi times mod psi. So this has to be something similar. And where this is a decreasing function vanishing at infinity. Theta is a non-negative decreasing function vanishing at infinity. And under what conditions we can find a compactly supported function whose Fourier transform satisfies this condition. And he proved that that is possible if and only if this integral is finite. Integral of theta t by t from 1 to infinity is finite. This is if and only if. So if theta is, say for example, theta is a constant, this integral is infinite. So we know that f cannot be compactly supported. So we can take any other function for which this integral is infinite, then we cannot construct a compactly supported function. Yeah.
The slides are not moving here, so I don't know if there is some time lag, or maybe you have to stop sharing and share again. Maybe there's some. Now it's okay. Yeah.
Is it okay now?
No, now it's gone, but it was beginning to.
Let me share again. Do you see this?
Yeah, now it's, yes.
No, where is my full screen? Open to full screen. Is it full screen now? Do you see the slides? Full screen?
Try to move the slide. I don't know if the problem has to do with the full screen mode. So if you try moving the slide, we can see.
Next.
Yeah, it's okay.
Okay. So in order to prove, okay, let me go to the, so this is a theorem. So we are looking for a compactly supported function whose Fourier transform decays like this. And Ingham proved that it is possible if and only if theta is integrable. I mean, theta is integrable with respect to this measure, dt by t. So how did he prove? So this is, let's call that the Ingham type decay on the Fourier transform side. So this is what I mean, Ingham type decay. And this is related to quasi-analyticity of the function. And recall, if f is an analytic function, if all the derivatives of the function vanish at a single point, then f is 0. That we know that by uniqueness theorem for holomorphic functions or analytic functions. But there are functions which are not necessarily analytic but having this property, and such functions are called quasi-analytic. Precisely, the function is quasi-analytic if f and all its derivatives vanishing at a point implies f equal to 0. So there is a relation between Ingham type decay on the Fourier transform side and quasi-analyticity on the function side. And the connection is by Denjoy-Carleman theorem. And Ingham used this idea.
Question out of ignorance. So what would be an example of a quasi-analytic function which is not
No,
analytic?
it is difficult to construct. It is difficult
Okay.
the existence has been proved, but then we will see several sufficient conditions on a function which will guarantee that that function is, because if the function is quasi-analytic and if it vanishes at all the points, it has to be zero. So existence has to be proved.
Yeah.
So that is in a paper of Borel. So
okay.
So
Thank you.
Denjoy-Carleman theorem says that if you have a smooth function, all the derivatives are bounded by, I mean, the L infinity norm of the derivative, and the derivative is bounded by some constant depending on f to the power n times another constant. And so this class is going to be quasi-analytic if and only if this condition is satisfied. The summation mn power minus 1 over n is infinite. This series diverges. So this we will call the Carleman condition. So this is one way of constructing quasi-analytic. We can find functions. We should start with any C infinity functions whose nth derivative satisfies these conditions. Then that is going to be quasi-analytic, provided this series diverges. But again, constructing that function is not obvious. So this was a one-dimensional case, but then well, we can ask the n-dimensional version, and then the whole story started when Mithun Bhaumik, Swagato Ray, and Suparna Sen started looking at this n-dimensional version of Denjoy-Carleman theorem, and I mean actually n-dimensional version of Ingham's theorem, and then they sort of they got hold of an n-dimensional version of Denjoy-Carleman theorem, and then proved an Ingham's theorem for Rn. This is not difficult. The theorem is the same. Theta is an increasing, I mean, it's a decreasing function vanishing at infinity. That is a standard condition we assume all the time. And this is Ingham type decay. So we want to know the function, the Fourier transform. Is it possible to construct a compactly supported function whose Fourier transform has Ingham type decay? And the theorem is it's possible if and only if this integral is finite. Actually, one can prove more. Under the assumption that this integral is infinite, that is 1 to infinity theta t inverse dt is infinite, then I mean the f cannot have compact support, that is Ingham's theorem, but f also cannot vanish on any open set. It is a slightly stronger version of Ingham's theorem. Anyway, Ingham's proof also gives the same thing, even though he didn't write it that way. So they proved it, the n-dimensional case. So it's natural to ask different versions of Ingham's theorem when the Fourier transform is replaced by Fourier transform on other groups. And also we can view this as a property of the spectral projections, and then we can replace a Laplacian by other elliptic or subelliptic operators. So let's look at this Ingham's theorem on R itself. And then by combining this f hat lambda e power I lambda x and then f hat minus lambda with e power minus I lambda x, call it p lambda f. And these are eigenfunctions of the ordinary Laplacian in one variable with eigenvalue minus lambda square. So that way this p lambda f that is given by this is nothing but the spectral projection associated to the Laplacian. So similar thing holds for Rn. So these are the eigenfunctions with eigenvalue minus lambda squared, and Ingham type decay gives p lambda f as this decay. The spectral projections have this pointwise decay. Yes, lambda goes to infinity. And if this condition 1 to infinity theta t inverse dt is infinite, then f cannot vanish on an open set, on an open interval. So that is the conclusion. When the spectral projections have this Ingham type decay, where theta satisfies this condition, then f cannot vanish on any open interval unless it is 0. So we will try to generalize this version to various elliptic operators and also for various Fourier transform. So replace the Laplacian by other elliptic differential operators, and then also Ingham type theorem for spectral projections. So these are two versions. So in proving all this, or in the study of Ingham's theorem or this for spectral projections or Fourier transform, this theorem plays an important role. So this is, we can think of this as the n-dimensional generalization of Denjoy-Carleman theorem. Denjoy-Carleman theorem for one variable case. And so we have these nth derivatives, but then the decay is measured after taking the L infinity norm. And here is a theorem due to Chernoff. You take n-dimensional functions on Rn, but then instead of taking derivatives, you can apply powers of the Laplacian. So we want to assume that all the powers of Laplacian apply to F are in L2. And then this is the condition. This is like the Denjoy-Carleman condition. The L2 norm of, instead of L infinity norm, we use L2 norm here. L2 norm of this guy to the power minus 1 over 2m, that's series diverges. We call it the Carleman condition. Suppose f is a function satisfying this condition. Then he proved that f is quasi-analytic. F and all its partial derivatives vanishing at a point implies f is identically 0. So this theorem plays an important role. Well, actually, most of the proofs of Ingham theorem uses this theorem, a version of this theorem, actually a weaker version of this theorem. Here, f and all its partial derivatives vanishing at a point implies f is 0. But if we can prove that f vanishes on an open set, then f is 0. That is a weaker version. That is good enough for Ingham's theorem. So in the n-dimensional case, this is the inversion formula. Fourier transform writing in polar coordinates. Integral, we write it in integral over Rn in polar coordinates as f at of lambda omega e power I lambda omega dot x, the measure on Sn minus 1. And then this is the lambda per n minus 1 d lambda is the decomposition of the Lebesgue measure. And then after integrating out with respect to the omega variable, what I get is a convolution with a function phi lambda that is explicit, that is given by the Bessel function Jn by 2 minus 1. This is the function, and these are known to be eigenfunctions of the Laplacian with eigenvalue minus lambda squared. In the one-dimensional case, we have this e power I lambda x plus e power minus I lambda x, that is 2i sine or cosine lambda x, that is the Bessel function. So n equal to 1, it is half minus 1, j half minus 1 is j minus half, that is cosine. So these are eigenfunctions, and these are the spectral projections. And this is Fourier inversion. If you view it as an inversion formula, we can also think of this as a spectral resolution of the self-adjoint operator Laplacian. So if I look at a version of Ingham's theorem for the spectral projections on Rn, just look at this theorem. Theta is the usual theta. We are assuming that this guy is not integrable. Theta tt inverse is not integrable from 1 to infinity. So f is a non-trivial function vanishing on an open set. We are looking at that. So is it possible to have this spectral projections having this decay? So Ingham's theorem says that it is not possible, but then we have improved this result by saying that the spectral projections for x coming from V cannot vanish. I mean, this is enough to assume that this Ingham type decay holds on the set V on which the function vanishes. We don't have to assume that this is true for every x, but only on the set over which f vanishes. Even this weaker assumption implies that f equal to 0. So this is it's an improvement. And similarly,
so in the previous thing of Chernoff, there was some, so it was a condition on some polyharmonic operators, no, like Laplacian M or something.
Yeah, Laplacian M, apply the powers of Laplacian. All those guys should be in L2. They're L2 norm to the power minus 1 over 2n. That should
diverge. How do you see the condition on, because in both conditions, Denjoy and the Chernoff, there were like conditions on the derivative or some combination of the derivative. So how do you see?
No, you cannot see. There is a big theorem in between.
Yeah.
So Chernoff's theorem and Denjoy-Carleman, there is something in between, because in order to show that all the derivatives of the function vanishing at 0, that is equivalent to saying that all the polynomials, all the monomials times f, these they integrate to 0. That is the density of certain polynomials. So there is a connection between Chernoff's theorem and the density of polynomials. that we will state that theorem, but we will not prove it. So through that only we have to work. So there is it's not immediate to see that the Chernoff implies Ingham. It's not obvious. There is a theorem in between. But here I'm just reiterating the fact that this decay, earlier we said that the spectral projections cannot have this decay for all x. But here I'm saying that even if the decay holds for all x in V is a set on which F vanishes, then F has to vanish everywhere. We can also replace this condition by the decay on this complement of V. Then also it is not possible. I mean, under the assumption that V contains the origin. So this is something unexpected.
Thank you.
Yeah, I just wanted to. I mean, this is sort of an incomplete survey. So since the time is 1 hour, well, as I said, I gave this talk in some other context. So there was a 1 hour time limit. So I just selected some results. So that was only RN case. I just wanted to say the spectral projection result. But then there is this Riemannian symmetric spaces of non-compact type. Again, 1 or 2 results I will mention here. And then I will go to the Heisenberg group, a couple of results, and that should be. So there won't be any proofs. So here, I think if you are not familiar with Riemannian symmetric spaces of non-compact type, just forget about that. Just consider this upper half space, H2, set of all xy with y positive. And there is some Riemannian metric with respect to which becomes a Riemannian manifold. And we can also realize this as this quotient, SL to R, this 2 by 2 matrices with the determinant 1. And this is the orthogonal matrix, take the quotient. And the Laplacian on this on this Riemannian manifold is ordinary Laplacian times y power minus 2. So there is a natural, although this Iwasawa decomposition, etc., you forget about that. So there is a Fourier transform and there is a Laplacian. So there is a Fourier transform. So we can ask, is there any Ingham type theorem for the Fourier transform on this space? And there is a Laplacian here. Is there any? I didn't mention. Where is the Laplacian? Laplacian is coming. So there is a Laplacian here, delta x, and this is a more general case, Laplacian. So we can ask for Chernoff's theorem for the Laplacian. So here is the Chernoff type theorem for Riemannian symmetric spaces of non-compact type. So in place of the ordinary Laplacian, you replace that by this Laplacian or Laplace-Beltrami operator. If it's a smooth function on this manifold, all these guys should be in L2. Take the L2 norm to the power minus 1 over 2n, and then the series diverges. Then Chernoff's theorem, we expect this, if f and all its derivatives vanish at certain point, then f has to be 0. That problem is, I mean, in this paper, they were not able to do that. So what they proved is, if f vanishes on a non-empty open set, then f is identically 0. I'm just going historically. So this is the first result proved on non-compact Riemannian symmetric spaces. So they have to assume that f vanishes on a non-empty open set, instead of assuming that f and all its derivatives vanishing at a single point. But this is good enough for proving the Ingham's theorem. So, and the functions on this space are sort of right k invariant functions on the group G. But if you impose some extra assumption, so what is the assumption? You assume that instead of assuming that the function is only right k invariant, you also assume that the function is left k invariant as well as right k invariant. Then we call them k bi-invariant, sort of radial functions, analog of spherical functions, radial functions. And then the all differential operators, all derivatives, that has to be replaced by all differential operators coming from this, all G invariant differential operators on the space. So again, let's not get into the details. And this is the theorem they proved. But here, so I said that the real Chernoff's theorem will say that if f and all its derivatives vanishing at a point will imply f is 0. That is not known. But if f vanishes on a non-empty open set under this condition, f is 0. That's what they proved. But here, instead of considering all functions, just consider k bi-invariant functions on the group G. or left k invariant functions on the symmetric space, then it's enough to assume that all the derivatives of f, all the derivatives in the sense that d coming from this d of g mod k, all g invariant differential operators on the space, all these guys vanishing at a single point, then f is identically 0. This is well, this is still not, this is the expected result, but there is a serious condition on the function. Function has to be k bi-invariant. But recently this bi-invariant condition has been removed by a theorem by Rudra Sarkar. I think I didn't include it, but, so let's not get into that. So what we have proved, I mean, before, after these theorems of Swagato and Mithun, and then before the theorem of Rudra Sarkar, what we have proved, we means with Pritham and Ramesh Manna, what we have proved is the rank 1 case. Instead of considering the general Riemannian symmetric spaces, we consider rank 1 case. Rank 1's case, there is this abelian part of the Lie algebra that is one-dimensional. So there is a single element there, and this single element generates a single differential operator. I will call it H. So this is the differential operator coming from this abelian part of the Lie algebra. So what we have proved is that take this to be a rank 1 symmetric space, and the usual condition, all the derivatives, all the powers of the Laplacian are in L2, applied to f are in L2, and this condition is satisfied. But if all the powers of H applied to f evaluated at x naught at a single point are 0, then f is identically 0. So this is Chernov's theorem for rank 1 symmetric spaces, but not for arbitrary symmetric spaces. So arbitrary symmetric spaces, that theorem was proved after this paper by Rudra Sarkar. And this condition is natural because, I mean, because this is the analog of the Euclidean counterpart. So in the Euclidean case, write f in polar coordinates, take the d by dr to the power k, that will give me summation mod alpha equal to k ordinary derivatives at r omega power alpha. So the radial derivative is vanishing at r equal to 0 is equivalent to saying that all the derivatives vanishing at this 0. These are equivalent. So therefore, in the case of rank 1 symmetric spaces, we thought this is the natural condition to impose on the functions. So all the h power l applied to f, they should vanish at the identity coset. Then that's what we assume. Then it is identically 0. So this is the rank 1 case. Well, on symmetric spaces, there is an analog of the Fourier transform. It is known as the Helgason Fourier transform. So once we have a Chernov's theorem, then we can prove it's an eigen Ingham's theorem for the Helgason Fourier transform. Anyway, this was also considered by Pusti, Mithun, and Swagato. So this is the Fourier transform. And then this is inversion formula. So this plays the roles of the exponentials. These are eigenfunctions of the Laplace-Beltrami operator. And this is the inversion formula. It is more complicated because it has, instead of lambda power n minus 1, some function is coming. This is the famous Harishchandra C function. So this is a Fourier transform. This is the inversion formula. And then spectral projection. I think I'm going to state the results for spectral projections associated to this Fourier transform. So again, the inversion formula I can rewrite, defining the spectral projections. These are going to be eigenfunctions of the Laplace-Beltrami operators. And these are all explicitly known. At least in rank 1 cases, these are given by Jacobi functions. Like the Euclidean case, these are given by Bessel functions. And this is inversion formula. So you can think of this as inversion formula for the Helgason Fourier transform or the spectral decomposition for the Laplace-Beltrami operator. So these are eigenfunctions with eigenvalue lambda squared plus rho squared. And then this is what we have. So this is the condition. So this is the analog of the theorem. So for the Rn case, it was not difficult to prove. And this is the real theorem in this paper. So this is theta usual condition. Integral is infinite. Then take a function vanishing on an open set. Then this decay is not possible on V. So this kind of decay is not possible on V unless the function vanishes. And if V contains the identity coset, then this estimate is not possible even on the V complement. So we don't have to assume that the decay holds for all values of X. So this is the, well, I stated it in the case of Rn, but Rn case is easy, but this is the theorem. And then one can also state, once we have a theorem for spectral projections, then one can prove Ingham's theorem for the Fourier transform. So that is easy to deduce. And this is again, the result is sure, because if we assume that this integral is finite, then there is a compactly supported K bi-invariant function whose spectral projections have this kind of decay. So this is a sharp result, similar to Ingham's theorem, but then only thing is now we only have to assume that Ingham type decay holds, assumed to hold only on the set over which the function is known to vanish. So this is a stronger result. Well, the same conclusion under a weaker hypothesis, so the result is stronger. And this is what I said about Ingham's theorem for the Helgason Fourier transform. So this can be deduced from the spectral projection theorem. So this is the Fourier transform. This kind of Ingham type decay is not possible if, well, if this is assumed, then under the assumption that this integral is infinite, then F cannot vanish on a nonempty open set. If it vanishes, then F has to be 0. So that is the theorem. This can be deduced easily. So finally, I will come to the Heisenberg group. So there are still some open problems. So Riemannian symmetric spaces, I think, as I said, Rutra-Sarkar's theorem gives the Chernov's theorem now, complete analog of Chernov's theorem. So it is sort of complete. So once we have a Chernov's theorem, then we have Ingham's theorem. So that is done. So let's consider the Heisenberg group. So this is Cn cross R with this group law. So this is Cn, this is R, and then the addition in Cn is just addition. The last variable, there is T plus S plus something extra. And this extra makes this group non-abelian, and it is a step 2 nilpotent group. Fortunately, the Lebesgue measure plays the role of the Haar measure. So the Fourier transform, well, in order to define the Fourier transform, then one has to talk about irreducible unitary representations of the group. And these are the representations, irreducible unitary representations. And fortunately, all these things are explicitly known. All these are unitary operators. Fix Z and T coming from the Heisenberg group. So these guys are supposed to be unitary operators, all acting on L2 of Rn. And the action is given by this. For I lambda T, so the central variable is just multiplication by this. The other variable, there is a translation of the function by y, and there is a modulation. For I lambda x dot psi plus half x dot y. So it is easy to see that these are unitary operators. It has to be checked that it's a representation and it is irreducible. So these are all well known. And then in order to define the Fourier transform, you have to integrate the function against these unitary operators. These are operators. This is a function I'm integrating. So I will end up with an operator. That operator is a bounded linear operator acting on L2 of Rn. So Fourier transform is an operator valued function. And then what is the Laplacian or sub-Laplacian here? So in order to do that, one has to go to the Lie algebra. We have to consider left invariant differential operators, first order differential operators, which are left invariant under the action of the group. And this is 2n plus 1 dimensional algebra. And the basis is provided by this d by dxj plus half yj d by dt, d by dyj minus half xj d by dt, and then d by dt. Just remember, look at that when x equal to 0, x equal to 0, y equal to 0, t equal to 0. At the origin, this reduces the ordinary derivatives. So these are the left invariant things. And this is the sub-Laplacian. Simply take sum of squares of equal to 1 t n, not infinity. Sum of squares of these and these. These are called the horizontal vector fields. This is the sub-Laplacian. And then add t squared and get the full Laplacian. So we can ask questions like Chernov's theorem for the sub-Laplacian. You can ask for Chernov's theorem for the full Laplacian. can ask for Ingham's theorem for the Fourier transform on the Heisenberg group. So there are 3 problems here. Well, the Fourier transform is operator valued. Then you should know how to measure the decay of the Fourier transform. So in order to motivate, look at this Euclidean case, the relation between the Fourier transform of a function and Fourier transform of the Laplacian of applied to the function, that is given by this. Laplacian f, take the Fourier transform, is f hat of psi times mod psi square. And the analog in this case of the Heisenberg group is apply the Laplacian to function f and take the Fourier transform at lambda. This is an operator. That is same thing as taking the Fourier transform, it's an operator, multiplying that by this unbounded operator, h of lambda plus lambda squared, and this is the Hermite operator. So in measuring the decay, we are using the sort of the semi-group generated by this Laplacian, or measuring in terms of the exponential of this guy. This is exponential of minus some function of mod psi. So here, the Fourier transform case, so we can write this in this form. F hat of psi bar, f hat of psi is less than or equal to e power minus 2 theta something. So here, this is operator. Look at this non-negative operator, f hat lambda star, f hat lambda. And then this has to be compared with another non-negative operator. So the non-negative operator we need to use is the sort of the semi-group generated by this square root of the Hermite operator. So this is the, forget the theta, this is the semi-group generated by the square root of h lambda. So this is the decay condition we have to impose. Because Fourier transform is operator valued. So one has to compare this with another non-negative operator, and this is the operator. So if I make this comparison, you can ask the question, if it's a compactly supported functions, under what conditions on theta we can construct a compactly supported function whose Fourier transform has this kind of decay. So that is the result. Theta, the same assumption. Assume that, not assuming. Then there exists a non-zero compactly supported continuous function whose Fourier transform satisfies this estimate. Fourier transform satisfies this estimate if and only if this integral is finite. Same thing like this. So this is the exact analog of Ingham's theorem. But I'm using full Laplacian, not the sub-Laplacian case. In the case integral 1 to infinity theta t inverse equal to infinity, then if this condition is satisfied and if f vanishes on an open set, then we want to conclude f is 0. And that is again, so that theorem we have proved only for the full Laplacian. So they'll say theta same condition under this integral being infinite. The Fourier transform satisfies this condition, then f cannot vanish on any non-empty open set unless it is identically 0. So this also we have, but then here we just remember that we have to use this condition. So this is equivalent to considering, well, in terms of the Chernov's theorem. So this is equivalent to proving a Chernov's theorem for full Laplacian. So that in order to deduce this, we have to use this theorem. That's what I mean. So this is the Chernov's theorem for the full Laplacian, but this is not the original version of Chernov's theorem, but the weaker version. So this is the Chernow condition, but then f is assumed to vanish on a non-empty open set, like the Riemannian symmetric space before Rudra-Sarkar. One has to assume that f vanishes on an open set, then it is identically 0 under this condition. So we have only proved this. So the problem of proving, arriving at the same conclusion, that is f is identically 0 under the assumption that f and all its derivatives vanishing at a point, that is still open. That is one open problem. And also we are using full Laplacian, but in the case of the Heisenberg group, we would like to prove such a theorem for the sub-Laplacian. That is still open. So these are a couple of open problems. And then, as I said, the spectral projections theorem. We had the spectral projection result for the Laplacian on Rn, Laplacian on symmetric spaces. Then we have something for the operators, two operators related to the sub-Laplacian on the Heisenberg group. So that these two operators are L and H. and this is the relation. So this is the Euclidean Fourier transform of the sublaplacian applied to f. That is the Fourier transform. This is an operator and this is the operator, h equal to this. So that is a relation. But we can also apply the sublaplacian to a function of z times exponential it. And that gives you another operator L related by this, defined by this way. And this is this operator. This is special Hermite. This is Hermite, special Hermite. And both operators, both cases, then we have a well-defined spectral theorem. Spectral projections are explicitly known and well studied. So we can ask the spectral projection version of Ingham's theorem. So these are, I think I'm going to skip all these things, all these details. These are the eigenfunctions of the special Hermite operator. And the special Hermite expansion will look like this. And this can be put in a compact form by defining the Laguerre functions. So these are special Hermite functions. And we can combine them. And then they will simplify into Laguerre functions of type n minus 1. And then let's go here. These spectral projections associated to the special Hermite operator are simply given by f cross. This is another convolution with this function. This is the Laguerre function. And this is the ordinary convolution with the extra twist. So this is twisted convolution. So this is a spectral projections. We can ask, this is a perceivable identity. F is given by this expansion. L2 norm is given by this. This is the Perceval's theorem or Plancherel theorem. Now this question is, what can you say? Assuming that f is non-trivial and vanishing on an open set, V, what is the best possible decay of the spectral projections? So replacing the Laplacian by this special Hermite operator. And this decay has to be measured in terms of the eigenvalues. Eigenvalues are 2k plus n. And this is the theorem, L2 version. So under this non-integrability condition on theta, the L2 function whose spectral projection satisfy this condition, then cannot vanish on a non-empty open set. Any non-trivial function whose spectral projections have this kind of decay cannot vanish on a non-empty set. That is the theorem. And this is an L2 version, but there is also a pointwise version. You can also assume the result pointwise. And this, when you go to the pointwise, we can enough to assume that this condition is satisfied only on this set over which f vanishes. Again, this is stronger version. So these are the two theorems for the spectral projections associated to the special Hermite operator. And similarly, we have theorems for the Hermite case. I think I have finished my time. Well, these are some of the references. As I said, oh no, sorry. I just gave only the references of my work with my student and who else? Ramesh Manna. Where is Ramesh? No, there are some. Yeah, this Shahin Bakshi, Jayanta Sarkar, Ramesh Manna, these are all there. So these are the things, but then other people are Sanjay Pushti, Mithun Bhaumik, and Swagatori, and Rudra Sarkar. So with Rudra Sarkar's theorem that symmetric spaces case, Chernov's theorem has been completed, but the Heisenberg group case still open. So that's all.
Thank you very much for the nice talk. And so if anyone among the audience has a question, please go ahead. It seems no, but I have some like general questions, meaning so maybe, I mean, since a long time I've been wanting to know why people like to do things in symmetric spaces or rank 1 symmetric spaces and Heisenberg group. So if you can just give me a few, meaning idea of why one does it, and maybe some references where I can read further, so I would be happy.
Yeah, Heisenberg groups you can easily pick up, but if you want to look at the symmetric spaces, then a lot of preparation is needed. So I won't suggest Heisenberg groups. You can look at some basic books like Folland's book or my book on the Heisenberg group, and then you can just pick up any paper on these topics with Pritham and others. Then can start reading. It's very simple. Heisenberg group is very simple. Representation theory is trivial almost. But if you want to do it on semi-simple Lie groups and symmetric spaces, the representation theory itself will take maybe a 2-semester course. So getting into that is non-trivial. But maybe one can just look at SL2R. There are some nice books on SL2R, like Sugira's book, Serge Lang's book. There are Michael Taylor's book, Non-Commutative Harmonic Analysis. So these things are there. I mean, these groups naturally occur even in applications. But then you have to look at some books by Audrey Terras, Non-Commutative Harmonic Analysis with Applications. He explains where these non-commutative groups are naturally occurring in applications. For example, Heisenberg group has connections with this radar ambiguity functions, what we call Fourier-Wigner transform in this radar technology. When you measure sending some sound waves and get it reflected and then analyze that, then the Heisenberg group naturally occurs. Because within mathematics, then it has so many connections, several complex variables, and so many. I mean,
you can send me at least a couple of references by mail, meaning the names. I can look at it. Like I try to find it myself. So, I mean, the one is non-commutative.
Non-commutative harmonic analysis by Michael Taylor. You just look at that book.
Okay.
Non-commutative harmonic analysis by Michael Taylor. It has SL2R, Heisenberg group, all those things.
Okay.
And that will have all the references you need. If you just stick to one book and then read it completely, then you can. But directly getting into semi-simple theory will be difficult.
Yeah. And I think I asked you somewhere in the beginning if you can explain and by the way, I think some of the things which I am meaning in a different context, I heard a talk in some conference by Yves Meyer. So he was talking about some recent results where the uncertainty principle was studied at the level of the support of the function and its Fourier transform instead of the decay of the. So I don't know if you have some.
No, once you on the Fourier transform side of assume that your Fourier transform has compact support. That is the best possible decay we can. But instead of measuring it in terms of support, we can also measure in terms of Gaussian decay or exponential decay. That is another way of doing that. Or integrability with respect to say x squared or mod psi squared. That is the original Heisenberg's uncertainty principle. Original thing. And then Hardy's theorem is in terms of Gaussian decay with specified specified variants, e power minus a mod psi squared, e power minus b mod x squared, like that. And then there is, in terms of the measures of the support also, there are theorems.
That was
there are so many variations, whatever you want to consider.
Thank you.
Although don't generalize to other settings, a lot of open problems. If you want to generalize all the uncertainty principles in the case of Rn to other symmetric spaces or the nilpotent case, then even formulation is difficult. There are a lot of problems.
Thank you very much. And so just before we close, meaning I would like to make special note of the fact that Professor Thangavelu has really formed a strong group on harmonic analysis, and many of his former students are becoming quite well known now. And I'm really happy that the harmonic analysis scenario in India is shaping up, and I wish we had someone like him here to also do things very interesting in such areas.
Okay, then thank you for attending. At least 3 or 4 non-Indians are there. The students are.
Yeah, some of them are students and some, I mean, one or two colleagues, and yeah.
Okay, muchas gracias.
See you. Thanks.
See you.
Bye-bye.
Bye.
Thanks, Professor. Thank you very much.
Yeah. Thanks, Ravi.
You will be getting the notifications. So if you want, you can, or if you have time, you can attend the future talks.
Yeah.
Yeah.
I
Thanks
wanted to
again.
ask
Yeah.
the Hermite